Today, we're going to dive deep into one of the most important, but probably least known components in the entire world, the MOS capacitor. It's the invisible engine that's powering pretty much every single piece of technology you own. So let's get right into it.
But before we do, let me throw a question at you. When you think about the most important inventions ever, what pops into your head? The wheel, right? Maybe the printing press? But what about the most important switch?
Well, the answer is the very device we're talking about. It's the fundamental building block of all modern electronics. And as you're watching this, you are using literally billions of them, maybe even trillions. They're inside your computer, your phone, the screen you're looking at, everything.
That's because this tiny little component is, at its heart, the switch that powers our entire digital world. So how does this microscopic powerhouse actually work? Well, the simplest way to think about it is like a tiny, super controllable gate for electricity. You can tell it exactly when to let the current flow and when to stop it.
To really understand how that gate works, we need to zoom way in and look at its structure. So let's dissect the anatomy of this microswitch. So what does MOS even stand for? Well, it's actually an acronym for its three layers. You've got a metal gate on top, then a super thin oxide layer that acts as an insulator, and at the bottom a semiconductor base. Metal, oxide, semiconductor. MOS. See? It's all right there in the name.
Let's actually build one from the ground up, just conceptually. We start with the foundation, which is the semiconductor substrate, usually a slice of silicon. On top of that, we grow a really thin insulating layer of oxide. And finally, we put a metal gate on top of it all. This gate is where we apply voltage to control the whole thing. And that's it. It's basically a simple three-layer sandwich. But the real magic isn't in the structure itself. It's in how we control it. Just by applying a little bit of voltage, we can make this device flip between three totally different states of operation. Here's the absolute key to understanding this. When you apply a voltage to that metal gate on top, you can either attract or push away the electrical charges in the semiconductor down below. This means you can completely change its electrical properties, and no physical parts have to move at all. It's all done with electric fields. You know what? To make this super clear, let's use an analogy. Think of the MOS capacitor like a water faucet. It's got three main settings. You've got water ready at the valve, you can turn it partially off, or you can crank it wide open and let the water flow freely. Okay, so this brings us to the three modes. First, there's accumulation. This is where we pull all the existing charges right up to the surface, ready to go. In our analogy, the water is ready at the faucet. Next is depletion. Here we push those charges away from the surface, creating an empty zone. The faucet is now partially off. And finally, the big one, inversion. We apply enough voltage to attract the opposite kind of charge, and they form a brand new path for electricity. The faucet is now flowing freely. This is the on state. So we have these three cool electrical states. But how do engineers actually see what's going on? I mean, how do you measure something that's happening on such a tiny scale to make sure it's working right? Well, we can't look at it directly, but we can measure its electrical fingerprint. It's called its capacitance voltage, or CV characteristic. Basically, by tracking how its ability to store a charge, that's its capacitance, changes as we tweak the voltage, we can map out exactly which state the device is in. So, let's trace this out. When the device is in that first state, accumulation, you have all these charges packed right up against that insulating layer. This means it can store a lot of charge, so its capacitance is at its maximum. Now, as we start to apply some voltage and enter the depletion state, we're pushing those charges away, right? We're creating an empty space. This empty gap makes it harder to store a charge, so the capacitance drops. And finally, when we apply enough voltage to create that new channel, that inversion state, the capacitance stops dropping. It just flatlines and stabilizes at a minimum value. This unique curve from max to min tells us everything we need to know about the device. In that one specific point on the graph, the exact voltage where we create that flowing freely inversion state, that point has a really important name. It's called the threshold voltage. It is the precise setting that officially flips our switch to on. Okay, we've gone pretty deep into the physics here. Let's zoom way back out. Why does this one tiny three-layer switch matter so much? How did it become the literal foundation of our modern world? Here's why. Because everything we've just talked about, that simple three-layer structure and its three states of control, is the absolute beating heart of the MOSFET transistor. And the MOSFET,
Well, that's the undisputed workhorse that runs our entire digital age. And its impact is just everywhere. It's the core of every single MOSFET device. It's the building block for all analog and digital computer chips. It's used in memory cells like the DRAM and flash in your computer and phone. It even enables tons of modern sensors. So why did this specific technology take over the world? It really comes down to three huge advantages. First, it takes almost no current to control the switch. Second, that directly leads to low power consumption, which is why your phone can last all day. And third, and this is the big one, it is incredibly scalable. You can make them ridiculously small, which is why we can cram billions of them onto a single chip. It all just boils down to this one simple fact, which is stated perfectly here. The MOS capacitor is a critical building block of modern electronics and semiconductor devices. It's not just important, it's absolutely fundamental. For over 50 years, we've just gotten better and better at controlling the flow of electrons with these tiny, elegant switches. We've built the entire information age on top of them, and it really leaves you with one massive question. Now that we've mastered this, what are we going to build next?